Now, let us first study the mole concept. For that, we need to understand what exactly a mole is. We have to understand that mole is 7th basic SI unit for the amount of substance. So, it is nothing but the basic SI unit for the amount of substance, which is usually taken for the microscopic particles such as electrons, protons, atoms, molecules or ions. So, now this is what it is. Now, it comes to the definition. I will take a balance. This is a simple balance in which at one side, say you kept the 14 gram weight. Now, when you kept 14 gram weight, that side of this balance will go down. Now, in order to compensate that, the other side, I kept on adding the nitrogen atoms till these two plates of the balance are balanced. So, that particular quantity or that particular collection of all the atoms whose weight is exactly equal to its atomic weight. Or if I take any molecule, suppose I have taken 44 gram weight at one side and say inducted or added CO2 or N2O molecules, so that these two plates get balanced, that is also referred as 1 mole. So, you can see 1 mole is the collection of all the atoms whose weight is equal to its atomic weight, or all the molecules whose weight is equal to its molecular weight. So, now this is the definition of 1 mole. So, as per this, mole is a collection, a number of all the atoms whose weight is equal to its atomic weight, or the molecules whose weight is equal to its molecular weight. Therefore, we conclude that 1 mole is equal to the atomic weight or the molar mass is equal to some constant of fixed value which is derived out of some experiments referred as the Avogadro number. So, this is the collection, that number of the particles whose weight has been happened to be the atomic weight referred as 1 mole, which we usually call as Avogadro number, or it is also referred as Avogadro constant. Now, this is exactly what 1 mole stands for. So, now 1 mole is the collection of all the atoms whose weight is equal to its atomic weight or molecular weight. So, 1 mole we replace always with this, such a huge quantity it is. 6 into 10 to the power 23 particles put together will give you 1 mole. Now, when we are referring to the atomic mass, now when we see the atomic weight of any element, suppose I have taken the carbon as a reference, the atomic weight of carbon is referred as either 12 AMU or 12 gram per mole. Now, we should understand the basic difference between the two. Now, when I am referring to the weight of 1 atom of carbon, I express that as atomic mass unit, whereas when I am referring to the weight of 1 mole of carbon, I refer that as gram per mole. So, when I am saying 12 gram, that indicates I am taking Avogadro number of carbon particles. So, now the relation between these two is given as the AMU definition is 1/12 of mass of each carbon atom is actually referred as 1 AMU. Even you can take this as 1/14 of mass of each nitrogen, or 1/16 of mass of each oxygen, or 1/32 of the each sulfur as well. Since I have taken carbon as the reference element, I am dividing this with 12. As we all know, just now saying that the mass of 6 into 10 power 23 carbon atoms is 12 gram, that is 1 mole. Therefore, mass of each carbon atom, now when we try to calculate, is, you can see, mass of each carbon atom is 12 upon Avogadro number. So, this getting cancelled. So, you take whatever, it anyways get cancelled. So, 1 AMU is always 1 upon the Avogadro constant. Now, when you simplify that, is going to be this much kilogram. So, this is the relationship between AMU, and when you are expressing the atomic mass, you should either express that in 12 AMU or gram per mole, depending upon the quantity of carbon atom that you have taken. So, now when it comes to a gas, when you try to find out or figure out the volume related to the 1 mole of the gas, that is what we refer as the molar volume. So, when we calculate the volume occupied by 1 mole of a gas is what we call as molar volume. Now, from the ideal gas equation, we all know that the number of moles can be calculated by using this formula, where P is the total pressure exerted by the gas, force per unit area, volume is the volume of the gas or volume of the container in which it is placed, N stands for number of moles, R is the universal gas constant, which is going to be a constant. Now, T is the absolute temperature, that is temperature taken in degree Kelvin. So, at standard conditions, I mean standard pressure and temperature, which otherwise referred as normal pressure and temperature. So, these are the conventions related to the chemistry, where we assume the pressure as 760 mm of mercury or 1 atmosphere or around 0.9 bar. The temperature is usually 0 degrees Celsius or 273 Kelvin. Now, volume occupied by 1 mole of the gas, hence when I substitute the value of N as 1, you will see that pressure, volume we are going to calculate related to 1 mole of the gas, molar volume, moles of the gas had been taken as 1, R value constant, and when you substitute, you are going to get the molar volume as 22.4 liter or 22,400 milliliter. So, this is the molar volume of the ideal gas calculated under standard temperature and pressure conditions or STP conditions. Therefore, when we conclude, we say 1 mole is always equal to Avogadro constant when it comes to the number of particles, or it could be the atomic weight if it is the atoms, or the molecular weight related to the molecules, or 22.4 liter related to the ideal gas under standard conditions. So, here onwards we are going to replace the mole with anything depending on our requirement. Now, in mole concept we are going to study the mass relationship, mass volume as well as volume volume relationship. Now, when it comes to the mass mass relation, we are going to learn. Now, in mole concept, first we are going to study the mass mass relationship. I mean, you are given the mass of one substance, you need to find out the mass of the other. Now, suppose you are given the copper oxide, say 79.5 gram. Now, 79.5 gram of copper oxide has how many gram of copper? Now, you can see clearly that the molar mass of copper oxide is 63.5 plus 16. That means 1 mole of copper oxide had been given to us. Now, since you have taken 1 mole of copper oxide, which has 1 mole of copper and 1 mole of oxygen put together. And as I told you, 1 mole corresponds to its atomic mass. So, 63.5 gram of copper and 16 gram of oxygen is present in this sample. So, now when you are given mass of the substance and the mass of other is being asked, you will find out this way. Now, if you take the examples further, say I have been given 50 gram of CaCO3, which is a solid, and I have been asked to find the mass of CaO and mass of carbon dioxide gases that are present in it. Now, how would I proceed? Now, since you are given CaCO3, which can be written as CaO and dot CO2 rather. Now, 1 mole of CaCO3 has 1 mole of CaO and 1 mole of CO2. Now, 1 mole of any substance is its molar mass, that is the molar mass of calcium plus atomic mass of calcium plus oxygen, 56 gram. So, mass of CaO is 56 gram. Similarly, 1 mole of CO2, that is the molar mass of CO2, 44 gram of CO2 is present in it. So, 44 gram of CO2 and 56 gram of the CaO, that is total, will give you the 100 gram of CaCO3. So, if you take 1 mole of CaCO3, this is going to be the situation. So, if you take 100 gram of CaCO3, this is going to be the situation. So, here in this you can see, instead of taking, we are going in the reverse direction, instead of taking 100 gram, we have taken 50 gram. So, everything is getting halved. You can see the mass of CaO that is present will be 56 by 2, that is 28 grams, and mass of CO2 that is present will be the 22 grams. So, that all depends how many grams of the substance you have taken, and accordingly we calculate the moles. So, since we have taken 50 gram, if I would have taken 100 gram of CaCO3, I would have got 56 grams. Since I got only 50 grams, I mean half of what should be taken, what should have been taken, we are getting the half of the answers. Now, when we look beyond this, say I have got sodium bicarbonate sample measuring 168 gram. When this is subjected to the heating, I have been asked to find the mass of Na2CO3 obtained. A simple question. You have been given 168 grams of sodium bicarbonate and you have been asked to find the mass of sodium carbonate. So, now when you have taken the sample, now you are linking the sodium bicarbonate with sodium carbonate, two different substances. It has been said that this upon heating gives rise to this. So, now you know that one sodium cannot give this 2 sodium atom on the other side. So, probably we may have to take 2 mole of the sodium bicarbonate. So, now this ratio 2:1 of these two substances, which is actually referred as the stoichiometric coefficient, indicates the mole ratio or volume ratio, but not mass ratio. You can take as a reference this pen. You can see that one pen has, the complete pen has one pen and one cap. Doesn't mean that the mass of these two is 1 gram and 1 gram, or if this is 10 gram, this is also 10 gram. So here the stoichiometric coefficient indicates just a number but not the mass. So we have to understand here you have been given the number ratio but not mass ratio. For every 2 molecules of sodium bicarbonate, you can expect 1 molecule of sodium carbonate. It's not that 2 gram gives rise to 1 gram. So the other substances, you can see there are 2 carbons, so other and hydrogen atoms has to be balanced. You can see there are hydrogen, there are no hydrogen this side, which always will be eliminated as H2O. You will see that the total mass is balanced. You can cross verify. 2 into 23 plus 1 plus 12 plus 3 into 16. This happened to be the molar mass of NaHCO3. When you multiply, you will see 2 into 84, that is 168 gram on the left side. On the right side, 2 into sodium 23, carbon 12, 3 into oxygen atom 16, 106 plus 12 plus 2 into 16, 44 plus H2O, 2 into 1 plus 16, that is 18, is again put together 168 gram. So by doing this, by balancing this, we are making sure that the mass conservation principle is being followed. Now this is a clear indication that if I take 2 mole of NaHCO3, I will be getting 1 mole of Na2CO3. I mean 1 mole corresponds to its molar mass. If I take 2 into 84 grams of sodium bicarbonate, gives rise to molar mass 106 gram Na2CO3. If I would have taken 168 grams of NaHCO3, surely it is going to give 106. Indeed, I have taken 168 grams of NaHCO3. So how much we can anticipate here? 106 gram of Na2CO3. Now if you want to find out the mass of carbon dioxide, you can see 2 mole giving rise to 1 mole, 168 giving rise to 44, 2 mole giving rise to 1 mole, 168 corresponds to 18. So the weight of other substances also can be calculated. You can see 44 gram, and weight of H2O obtained is 18 gram, and weight of sodium carbonate is nothing but its molar mass. So this way we find out the molar mass of each and every substance, the mass of each and every substance that is obtained when there is one reactant participating in the reaction. Now my dear friends, here the big doubt arises if a reaction goes to the completion and more than one reactant is involved. When more than one reactant is involved in a chemical reaction, which reactant will be completely consumed? Which reactant is going to give you the complete amount of the product? Which is going to sacrifice during the reaction is something that we will study in the name of limiting reagent. Now when the chemical reaction has more than one reactant involved and when it goes to the completion, so number of reactants are greater than or equal to 2, and if the reaction is presumed to be 100% over, then this concept is valid. So now this limiting reagent is the reactant that is completely consumed during a chemical reaction, completely finished during a chemical reaction. Now in order to understand this concept, let me take a reference of, say we are interested in making a moving car. Now for that we require the engine, body, and obviously in a ratio of 1 engine per body and 4 tires per car, and these are what are referred as stoichiometric coefficient, which do not indicate the mass ratio. It is not that sum of the mass of the 4 tires is equal to the mass of the body or mass of the body equal to the mass of the engine. Now suppose we have the 200 engine, we have 500 body, and we have say 100 tire only. Now based on this, if you want to really see, we are not making an auto here, we require definitely the 4 tires. So you can see one car require 4 tire. So therefore, how many we can make? 25 cars. So your tires will be completely consumed. And for 25 cars, you will require only 25 body. So the remaining is 500 minus 25. And 25 cars require only 25 engine. So these two are remaining at the end of the reaction. So these are what we refer as excess reagents that are remaining. These remain after the reaction. Whereas this is what we call as limiting reagent, is predicting how much product can be obtained and how much other reactants are going to react. So now when we change this little bit, now in the second case, say instead of taking 100 tires, what I will do is I will make this 500, I will make this 200, and I will make this. Now we want a complete set, so we can make 200 cars. So now we can see this is completely consumed, hence it is the limiting reagent. 200 requires how many tires? 800. But do we have 800? No. So could you please make out what could be the limiting reagent? Once again it is going to be the tires, right? So since the number is predominating here with respect to the stoichiometric coefficient, we always say that the reactant that is completely consumed is the limiting reagent. You know, understand this better. What I will do is I will make this now this time 1000 tires. Now when I am making this 1000 tires, as we could see that the body that are completely over 200. Now one body requires 4 tires, so 200 body requires 800, hence the remaining tires. Now this has turned out to be the excess reagent here, whereas this is the limiting reagent, and 100 engine will remain as well. So it could be either tire or body or engine. The one that is present lowest cannot be the reagent, rather that produces the lowest is actually the limiting reagent. So we can extend this definition. Limiting reagent is the reactant that produces the lowest. Among all the reactant that produces the lowest is actually the limiting reagent. Now let us take a genuine example, a chemical reaction, to explain this concept. Now let me take a chemical reaction where your marble chips have been dissolved in dilute HCl to give you this product. It has been asked to find out the mass of CaCl to obtain. Now when you are given say 100 gram of CaCO3 and 73 gram of HCl, you are given in this ratio. For every 100 gram you had been given 73 grams. Now we know from this ratio that for every 1 mole, that is 100 gram, how many moles? 73. Now in this case both have been taken in the appropriate ratios. Now both will be completely consumed. So 1 mole is giving rise to 1 mole, or 2 moles is giving rise to 1 mole. So therefore how many we can anticipate here? 1 mole of CaCl2, which is nothing but 111 gram. So this is going to be your answer. Now in this case, is there any limiting reagent? Obviously no, because both are equally and completely consumed. For every 1 mole you require 2 mole. 1 mole means 100 grams, 2 moles means 73 grams. 2 into 36.5. So both have been equally consumed, so there is no concept of limiting reagent. Now when I change the ratio little bit, now when I take 50 gram of CaCO3, let's see what's going to happen. So you know, for here 100 gram of CaCO3 and 73 gram of HCl will give you, as you have seen, 111 gram of CaCl2. Now since you have taken only 50 gram, that is how many mole? Half mole. 73 gram, that means how many mole? 2 mole. Now let's go to find out the limiting reagent. Now you can see here clearly, for every 1 mole how much has reacted? 2. For every half how much would go? 1. So the remaining will be 2 minus 1 mole. For every 1 mole you are getting 1 mole. For every half you will be getting what? Half mole of CaCl2. That is 111/2 gram of CaCl2 is obtained. Now when I take this as the limiting reagent, since it is getting completely consumed during the course of the reaction, where the other substance is remaining, you can see here. Instead, if I experiment this by taking the others as the limiting reagent, is it appropriate to say so? No, because 2 moles is require 1 mole of CaCO3, indeed you have taken only half. So 1 cannot be consumed out of half. So therefore this cannot be the limiting reagent. So what is the limiting reagent here? It is obviously going to be CaCO3. You can see CaCO3 is the limiting reagent which is producing the lowest amount of CaCl2.